اوكي. السلام عليكم ورحمة الله. طبعا اليوم الموافق 13. انا هتكلم بالعربي لكن المحاضرة ذاتها باللغة الإنجليزية يعني. اليوم السبت الموافق 13 يونيو. نحن سعداء انه يكون معنا في هذه الجلسة الدكتور مجدي أبو القاسم محمد، وهو IEEE member. He received his bachelor degree from University of Khartoum and the MS in computer science and his PhD in electrical and computer engineering. Both the MS and the PhD are from the Missouri, Columbia. He received his PhD in 1995. From 1985 to 1988, he worked as a teaching assistant at the Computer Center, University of Khartoum. At the same period, he worked at other places. For example, Computer Man, as an electrical and communication engineer, and also at Sudan National Broadcasting Corporation in Omdurman. From 1991 to 1995, he was a research and teaching assistant in the Department of Electrical and Computer Engineering, University of Missouri, Columbia. He also worked there as a visiting professor. He joined Motorola in 1996 and worked as a principal staff engineer at Motorola Labs. Motorola Labs Physical and Digital Realization Research Center of Excellence. He also worked in Illinois, and he was inducted into Motorola Science Advisory Board Association into brackets SABA in 2007. Dr. Muhammad worked as a technical director at NITTEK as chairing a group company in Sterling, Virginia. From 2008 to 2011, that's the period he was in Sterling, Virginia. From 2012 to 17, he worked as a principal engineer at Qualcomm, Inc., Multimedia, Research and Development, and Standards. His area of focus, computer vision, systems, the research and development, standard computer vision. These are all of his interest in San Diego, California. Recently, Dr. Muhammad established an initiative called Advanced Metrics for improving computer vision, pattern recognition, and machine learning techniques in San Diego, California. His research includes multimedia, automatic target recognition, line mine detection, real-time change detection, pipe inspection, offline or online handwriting recognition, optical motion, digital signal image and video processing, computer vision, fuzzy sets and systems, neural network, pattern recognition, parallel distributed computing, nonlinear and adaptive modeling techniques, machine intelligence, fractals and chaos structures, energy-aware processing, and context-aware computing. Dr. Muhammad was honored for outstanding research contribution with several awards, including a reward that he obtained or got in 2003, IEEE transaction on fuzzy systems, an outstanding paper award for the papers titled Generalized Hidden Markov Model, Part 1 and 2, presented by IEEE Neural Network Society in 2003. Welcome, Dr. Muhammad, and welcome everyone. I will be on mute, and the floor is yours, Dr. Mahdi. Thank you.
Assalamu alaikum. I'm going to share now the whole disk, right? Just want to make sure that you can see the slides before I start. Can you see my slides now?
Yes, we do. Yes, summary and yes. Okay, thank you.
So this is the second session that we started last time, session 2 out of 2. And I'm just going to continue describing some of the big systems and try to make more elaborations on the concepts we talked about last time and what motivates them, why there is big advancement in this field. And let me try to, because it's very hard to read from without a presentation mode. So now in presentation mode, this is the slide 62. We covered 61 slides first, and it's recorded. You can go and look at it if you like. I think it's you already distributed, yeah, right? The record of the first.
Yes, sure. Thank you.
Session. Okay, I can hear you. Can you hear me, Jad?
Yes, yes, we do.
Okay, so this story is actually greatly impacted by digital technology. And as you know, digital technology has great impact on memory, on processing, on the cloud, communications, on the sensors. A lot of things happen as a result of digitization and building digital systems. So I'm going to go a little bit on how that's impacted the computation intelligence and how we use it. So the digital technology allows us to do stuff that was very difficult to do a long time ago in real time. Now we can do a lot of things like natural language translation. When I speaking to you hear me talking to you in your language in real time. I understand your response, although you are not speaking my language. That the idea that we started with last session or the first session. The cloud, of course, communication is greatly enhanced because of that. But the focus for us is actually is intelligence, or what we call machine intelligence, or AI, or computation intelligence. We're gonna describe in more details some of the terminology and the capabilities of the existing solutions or technologies, if you like. So when we talked about intelligent systems, it's more than the model that we were constructing before. So if we have sensors and we have some sort of machine intelligence, we expect to get more advanced behavior of what we make as devices or as procedures and so forth. It's beyond automation. Automation may imply that something already predefined to deal with something in a specific way, but by the machine. Here we are asking the machine to reason about the environment and change behavior. So it's not just like the cruise button that you put, that's high automation for driving the car. But letting the car reason about what it sees and adapt depending on data, that's a new game. And to do so, it's more than the model. It's the whole system components. And I'm going to touch on that in this presentation. In general, when we talk about intelligence, we talk about some of the things that I mentioned before, better recognition, learning, how we are going to tune the parameters of the model, how we are going to do analysis. But we're also going to talk about synthesis today, how we are going to generate. When you hear the term generative GPT, for example, chat GPT, what do we mean by that? Although last time I talked about emotions, that those machines can actually understand the facial expressions and it can render in different languages emotions, but that's a different aspect. There's a lot of talk about consciousness, which is the machine conscious or not, or machine consciousness. I'm not going to talk about that because all we care about is to solve a problem. We have problems, we want better solutions than what we have. And we hope the machine can help to do so. So I'm trying to elaborate more on the term intelligence and compare shoulder to shoulder. What's human intelligence is, what's machine intelligence is, or some of the characteristics at least. As I said, machines are now digital, but they are consuming a lot of power actually. Analog system might consume lower power, but we lose the ability to store or copy information and share the models. And those models are very big. We're talking about just yesterday, I hear that's a company announcing a model that has 1 trillion parameters. So memory is important. Human intelligence secure. Here we have less secure, I would say, because people are working on that aspect to make it more secure. How many connections in the human brain, according to what I found, like 100 trillion connections compared to 1 trillion connections right now for the biggest machine we have. Both human and machines can be deceived. Okay, humans are able to perceive, machines can use sensors to perceive, whether they are optical, touch, whatever, you name it, you can perceive data. Well, it's conscious, humans is conscious, but there are people who are talking about that machine could be conscious in the future because of new technologies, and I'm not going to talk about that. The use case I talked about last time is distributed using multiple cameras. I'm going to touch on that today as well. And we want to track people with multiple cameras, but the system, even some of the cameras are down for any reason. And the processor connected to them is not working. We still want the machine to function. So it's not centralized, and that's an advantage. Okay, of course, we know this is biological, the human, and we are talking about man-made devices for the machine. And so forth. When we talk about the human intelligence, we use terms like wisdom. This is a wise man. Here we just want a clever solution. We don't necessarily call it a wise machine, but anyway, we need to deal with incomplete, ongoing, and we can tell there is something missing with humans very efficiently. And to deal actually with incomplete data, this is or noisy or vague or when frame drops, this is really some of the challenges that the machine need to address compared to human that are very advantageous in that respect. So let me try to put some of what we talked about last time, what we mean by a neural network, what's deep learning, convolution neural networks. Today, I'm going to talk a little bit about recurrent neural network and how those language models were built with some advanced architecture that's tried to solve the problem with the old machines, if you like. I talked about machine learning, which is the techniques that we use to do the parameter estimation. That's what learning is. So optimization in general, talk to support about support vector machines, classification, regression, those kind of tasks. So this is just a view graph to give you a feel about what we talked about last time, some of them, and what we are going to delve into in this session regarding natural language processing and understanding what we mean when we say processing, what we mean when we say understanding of the languages, visual perception in robots, some kind of new technologies that we call agents that's being used in robots and so forth. Well, I like the name computation intelligence compared to artificial intelligence because everything we do right now is by computer. And in the IEEE communities, computation intelligence contains three aspects or disciplines, if you like: neural networks, genetic computing, and the third part is fuzzy logic or logic in general. That's I was talking about last time. So I am in right now it's like 69 yet. Okay, can you hear me?
نعم. Yes.
Okay.
شكرا.
Okay. So who are the major players in this game? I just put some here, but of course there is more. And right now the competition is very tough, even from coming from the small companies. But you hear about what's OpenAI, GPT systems for natural language processing. Google has some products, IBM, Microsoft, you name it. Alexa from Amazon and Facebook is doing a lot of work for facial recognition or facial expressions, those kind of things. We can detect whether somebody is uh, smiling or angry or those kind of expressions by computer. Tesla is interested in the self-driving cars and the battery technology, particularly. NVIDIA is the GPU, the graphical processing units. And the data centers is the big thing because right now most of the number crunching for training those huge models is happening in the cloud, in data centers. Salesforce for chatbots, Adobe for imaging and video. But you hear about a company, for example, called Anthropic, which makes one of the most impressive machines right now. So reasoning, I'm gonna talk a little bit about general reasoning in this presentation, visual reasoning when we deal with video or images. And of course, there is multimodal when we have, for example, both audio and video, or some other modalities, audio, video, and touch, and so forth. Those are the kind of things that we need to do some reasoning about them, using techniques like pre-training, like you hear about chat GPT, G for generative pre-trained transformer architecture. I'm going to talk about that just to give you a feel about what are those things. Fine tuning, if you have your own data, you want to change the model slightly after being retrained, and what happens when we have more than one expert, how we going to combine or fuse them. I'm going to talk about the alignment problem and context and agents. So this is just like the agenda of today's talk, if you like. So I assume that most of you knows what's feed-forward neural networks. It's every time we have more than one layer, we call it deep. But the task is we do a weighted sum in each neuron, and we map it through a nonlinear activation function. And because if we just continue with the weighted sum, there is problems. This is going to be a linear model, and we cannot solve problems like X over C. And there is a lot of different kind of networks that's I need to. So the learning mechanism theory, if you like, up to now, the biggest thing is something called backpropagation, which is the optimization techniques when I have data. That's for supervised learning. I'm going to talk about supervised and unsupervised later. How we construct the model given a training set for building the machine. We want to construct it. Not just dealing with one input. We want to deal with sequences of inputs, like for handwriting recognition, for speech, we need to deal with time series. Even for the stock market, I know that some of the people attending today's session might be interested in how we are going to use this in predicting stock markets or doing any financial decision. So the story starts with something called long short-term memory. But when it becomes very long, there is a problem about training them when we compute the gradients. That's what we use in backpropagation. We face some numerical problems, which called the gradient decay. And new architectures came to solve, like the attention model, the transformer architecture. They came just to solve that problem so that we can deal with this problem. And we want to use the context, the previous information more wisely by just paying enough attention to the part of the sequence that has the information we think it's more useful. When we teach our students, most of you probably are teaching courses on neural networks. They give something like, yeah, what are those auto encoders, for example, which we try to teach a neural network to map X into itself, X. That's why it's autoencoders. And there is different kind of them, sparse, whatever, noising. And you probably heard about a lot of the old networks, Hopfield, Boltzmann machine, deep belief neural networks, and a lot of variation. And last time I talked about support vector machine, which is not intended actually to do time series analysis, but it's just for one vector. The algorithms to train support vector machine, it's very, very intriguing because it end up to be, instead of just a nonlinear program, it's a quadratic program, meaning we can afford to find the global optima. That's very impressive. But another advantage for support vector machine is each node is actually a data point, and it discovers for you how many nodes or support vectors you need. While in those other structures, you have to fix the number of input nodes, hidden nodes, and so forth. A lot of variation. We have, for example, residual network where we can skip and so forth. This is what it takes in practice to be a winner. It's very, very sophisticated, if I say this is what comes from DeepSeek. And he was challenging people in big corporate like NVIDIA and so by trying to come up with some systems that use GPUs, of course, for building the model, but in a very, very good engineering, I would say, how they train it, something called distillation techniques. So they train it with outputs from their competitors. And they were able to achieve much better performance by doing a lot of engineering work around the system, around how the user is going to prompt the network and how we are going to consume the context, right? So those kind of things make big difference. Even if you stick with the same model, you don't touch it. Although you want to change the model because some of the problems requires online learning while you are using those machines. You want them to be advanced next time you use them, or the same session but at later time. Neural networks are inspired, I would say, by the biological neurons. But we don't have to follow or fully do it the same way as the human does, because first of all, we don't know a lot of things, how humans pay attention, for example. It's very difficult to be understood from a neuroscience point of view. We wanted to come up with some tricks how to do the attention that's being used in some of the recent developments, if you like. It's all about data. And you can probably hear right now about new type of engineering or jobs. We call this guy a data engineer or a data analyst or a data scientist or a machine learning engineer. If we try to see what everybody is supposed to focus on, in like 12 dimensions attributes. And last time I said that is very hard to visualize in high dimension. This is just to give you 4 points in a 12 dimension space. So you can see that, for example, the machine learning engineer is supposed to do machine learning, definitely operation, develop the model, do the training, but he has to be aware of the other things as well, but not to the full level as you see here from this graph. And so forth. The data analyst, this guy is going to do the storytelling, sit with the customer and try to understand his story, what he's trying to accomplish, and do the visualization of the data, whatever he can do, and try to say, is this going to solve your business intent or not? And he's supposed to do some reporting using metrics or something like that. But I like this graph, but you can imagine if the number of dimensions increase is going to be smoother. That's not a big problem. But if I am talking about a lot of points, it's going to be very noisy. Still, visualization is a very, very difficult problem when we deal with high dimensional data, which is the norm rather than the exception. It's all about big data. So data science is supposed to present for me, at least in some meaningful manner, unstructured data. And to be able to do that, the technology used does a lot of things. Here, I'm not going to be able to read all of them, but I want to give you a feel about what it takes, starting from the fundamentals that we start with last time until we make a product or a toolbox in 10. And this story is changing. It's not like we fix it. That's what we should go. That's what we should follow every time to build a technology or to maintain an existing one. So you see where we do the machine learning, it's just this a small part of this big story. So I'm gonna elaborate a little bit about data because it's really what the model is all about. It's the data more than anything else. And this technology that we call intelligent machine or machine intelligence, the difference between that machine and the classical models where we use physics-based rules that we already understand and we try to build a machine. Here, we got data and we want to build a machine. For most of the time, phenomena that we don't know how physically they are happening yet. But we have observations, like in hidden Markov model, we just have observations and we try to come up with probability distributions to do classification, for example. And when I talked last time about the 3 tasks for machine, it's classification, regression, density estimation. That doesn't mean that every problem is just one of them. In the same machine, we could be doing more than one thing. And it's not just about supervised, unsupervised, or a hybrid technique, the same model could be using supervised, unsupervised, and a hybrid thing to get a better solution. So there is databases that people use to develop those pre-trained models, depending on your problem. If you are talking about blockchain, you have to be focusing on this kind of data. If you are dealing with time series, it's different than if you are dealing with static images versus video, for example, and so forth. I'm just trying to put in a one view graph the kind of the databases used for both constructing the model and validating whether it's good or not. I'm going to talk about how we do that. It's not just one thing we do and we say, okay, we are done. This seems to be working good, and commit to it. So, want to move from data to wisdom. This is just some cartoon representation of what we mean by knowledge. We want an answer to the how questions when we talk about information, who, what, when, where, those things that we call information used to be done long time ago with deterministic systems. Just the output is always the same, regardless of what happened to the data. To get to the level of wisdom of humans, what it means to us in the machine is what's the impact. If the impact is good, I was able to detect, for example, cancer in an image, or find a buried landmine and avoid a loss of life, that's a great impact. But usually we start with data, it's a label, we get information, give it some labels, the colors. Knowledge is the relationship, those links, if you like, between the data points. Inside is when we highlight part of it, we say this is, we pay more attention here for some reason, and the wisdom is you pay more attention and you find the connection. I hope this really give you a good visualization of what we want to be doing until we design a machine that's going, the machine itself is going to be creative, right? So how that's going to be done by computers? Add, multiply, divide, and a lookup table. That's the role of the machine intelligence, if you like. All right. We use mathematics, we use statistical methods to be able to accomplish the task that I mentioned in the previous slides. Someone asked me last time, what do you mean by machine learning? And I gave a very compact answer, but it's really a big question. It's like the core of this presentation today and last time is actually to show you what we mean when we say classification, regression, how we evaluate, what are the algorithms that's being used to do so, and what are the concepts. Just start from a conceptual description of what we want to accomplish until we have some realization of it. I showed you a support vector machine last time, and I changed some parameters. And I showed you that changing those parameters will change the behavior of the machine. We call them hyperparameters. What's the cost of calling something that's A? We call it not A. The misclassification has to be, we have to tell the machine that making this mistake is a big thing to this degree. And those hyperparameters to define the number of hidden nodes or the input nodes sometimes change the behavior significantly. So machine learning tasks are about all those kind of things. Training, how we are going to validate, make sure that this machine is ready for deployment, not just for toy problems in the lab. We want it to take it into the wild and run it over there. Some of the machines that I mentioned, like neural networks, people say it's a black box, meaning, hello? Hayat, it's slide 84, if you can see me.
Yes, yes, we do. We see machine learning, okay, and explainability, yes.
Right. So we love to have a machine that's the way it has meaning, like probabilistic hidden Markov model. Each part transition probability, something like that, by itself has a meaning. For neural networks, if you look at weight WIG by itself, it's hard to put a meaning, but we know that the whole weight just represent a separating hyperplane. So, but we wanted the model to be explainable to the user, not to the scientist, to the person who built it. And that's one of the big challenges for building a machine. The stuff that I presented in first session is actually explainable. Because, for example, Motorola want to understand when a call drop, why it's dropped. They don't like a black box solution. So we build those machines to be explainable, and that's a great advantage for the machine to have. Okay, what are the major algorithms for machine learning? We talked about slightly about supervised when we provide a teaching target for each input pattern. Unsupervised when we don't have those labels. And sometimes we have semi-supervised. For example, support vector machine, Vabnik, the founder, came up with a very interesting technique where you have labeled and unlabeled data, and you still want to train. So it's like a very challenging task, which part you trust more on how you are going to formulate this as a quadratic program and solve it. Talked about examples of classification regression. Clustering in machine learning, it's what's called density estimation in statistics. It's the same. Even right now for something like reinforcement learning, which kind of doing a hybrid thing, supervised and unsupervised together, there is still variation. Does it have a model or it doesn't have a model? How you formulate the learning problem is very different. Although the task is just to get a machine that solves the problem. And there is some specific ones that I listed here, just as an example, not to say that's all what we have. It's not for completeness, it's for just sake of discussion today. I want to give you a feel about what we all, what's the difference really when we talked about classification, regression? From a mathematical point of view, classification, when we wanted to find a separating hyperplane between two types of the inputs, class A, class B, for example. Regression, when I have some observation here in 1D, and we want to model them, for example, by a linear line here. But it's not necessarily linear. It could be any curve. We still want to find that curve, even when the data is very noisy. Clustering, which is unsupervised learning, which is like density estimation in statistics, is when we have data, but we don't have the labels. This is image has cancer or not. We just have the collection of the data, and we want the machine to give it a label. Whatever you want to do is that label, it depends on what problem you are addressing. For example, to do hidden Markov model, we start with this clustering to generate a code book. So every partitioning of the data or clustering of the data, we want to replace it by just one vector. And every time we see an unknown, we just pick the closest one to them, and we give it that label. So this is a clustering task. Even for the continuous density, that's for the discrete hidden mark. Even for the continuous density, to learn those Gaussian mixtures, we do clustering inside hidden Markov model when we are building the model to figure out how the data in high dimensional space should be treated. Reinforcement learning is a technique where we want the machine to learn from its mistake. Like in gaming, for example, if you lose in a move for a case, you want to don't repeat that kind of mistake again. And there is penalty to do so. Right, I just showing you here a typical example from what I did for handwriting recognition. To give you a feel that we use both supervised and unsupervised to solve the problem of cursive handwriting here, just for the sake of visualization. Those machines, the separating hyperplane, although we are going to talk about generative models later, which are not separating hyperplanes, they are distributions actually. They are very bad in after you find the separating hyperplane, if you give it a point that's very far from the separating hyperplane, it's not gonna say, I don't know. You want to do digit recognition, you give it 10, which is not a digit. It's not going to say, I don't know it. It's just going to pick one of the 10. So what we did is we clustered the whole digit data into 100 clusters. In clustering, one of the difficult problems is to fix the number of the clusters themselves. And we use something called self-organized maps, which is a clustering technique here. And what I'm showing you right now in each of those 10 by 10 map, this is the weights. Each here square is showing you the weights for the input. Because we want to get rid of garbage, so this unsupervised mechanism is used as a selection first layer to a feed forward supervised learning network. So it's both, we do this separate than the feed forward, but it's very natural. It tells us how gradual the change between class 0, class 6, the first row, 3. And if you go the first column from 0 to 4 to 9, and this is just what the machine told. So every time I give it an input, some of those nodes are going to be going to give high values depending on the hits. Whether we hits, if it's 8, we are going to be hitting on those nodes. And that's what we use as a feature vector to train the feed-forward classification network. It's just an example to tell you that to solve the problem, you will be using more than one of those machines. And that's where really big difference happens. If you don't do that, you just feed the input as is. We found that we can get very high classification when we show it a real digit. But when we show it something that's not a digit, it does a very bad job. So we want to be consistent, and because our segmentation is not going to be perfect, so we need a mechanism like that. So how we build those machines, which is the parameter estimation task. What I'm showing in front of you right now is something we call 20% jackknife procedure. So we partition the data randomly into 5 parts, 20%, 20%, 20%. We use 80% to build the model, and we test with the other 20%. And we keep repeating this 5 times until we make sure that the machine is doing the task. Here, the inputs are from X1 to X5. The output is, for example, class A or class B, the Y. So validation depends on whether it's classification or it's regression. In regression, we have some way of quantizing the error, mean square error, something like that. In classification, we look at indices. That's here I'm listing as sensitivity, accuracy, specificity, and so forth. So what are those numbers? Because those are the key, the guard that's going to tell me that my machine is good enough to be used. After that, I could use the full data to train the model and deploy it. But this is what's happening during building that model, if you like. Now I wanted to highlight what we call generative model, like ChatGPT, generative pre-trained transformer, or or so forth. As I said before, this discriminative models is just finding this line between class A and class B. And you find a lot of things: support vector machine, neural network, logistic regression, those kind of things. But what's called now generative model is a density estimator. Like hidden Markov model is a generative model. And the tough part in high dimensions, in 2 dimensions, we can judge, visually look at it. But in high dimensions, if I'm looking at data that's hundreds of features as input vectors, so we want to get that distribution. We cannot assume, say, it's Gaussian. We don't know, okay? So finding that distribution or the clusters in high dimension space, if you like, clustering computer science is an MB hard problem. Computer scientists understand what that means. Doesn't mean that we cannot do anything about it. We can do something, but we need to to test and validate how that hidden Markov model is good, that Gaussian mixture is good, that's Bayesian network, if you like, or deep belief network is good. So the term generative, instead of finding a separating hyperplane, is going to find the distribution. And that's good to reject something that's far from distribution one and distribution two, but is very difficult to build because it's unsupervised. Okay, I'm going to talk about languages because it's going to challenge all our time series analysis techniques. We want to make sure if we train for one language, we can consume in another language, because knowledge might be represented in one language, but not the other language. If we build it for each language separately, how we are going to combine, that's also a challenge for building natural language. By processing, sometimes we mean like the difference between video processing and video analysis, video analytics. So understanding the language is harder than just processing it. We can compress it, but understanding it, compress the language, or we can pick part of it, or we can search deterministically, that's processing. But here we're talking about the stochastics, about trying to get the meaning out of a sentence, whether it's handwritten or it's ASCII from a textbook, is still understanding the meaning is not an easy task for the machine. Well, this is just what's happening worldwide about those language models according to MIT. I'm not going to spend time here, but I want to give you a feel about the exploration that's happened since starting early 2018 up to now. If this is 2023, you see the developments are really, the big guys are paying a lot of attention to those language models because we can use them actually to deal with something that's not even language. Like right now we have models to do computer vision. It's not language per se, but we use language models to reason about those images. Tough competition. You can see what's happening between GPT from OpenAI, for example, those kind of things. And big things happen just sometimes because of gaming. AlphaGo, for example, is a game where somebody claimed, or some company claimed that we got a machine that can outperform the human, which is true. There is machines right now that can outperform humans because of the number crunching capabilities, huge memory, and the way we analyze time series. This is just to give you a feel about how tough the competitions. A company like DeepSeek just jumped into this space in 2024. And it challenged the big guys, Google, OpenAI, in terms of performance. That's very tough. So they are not just claiming, saying we are better. They are showing numbers, and you can test their model to find that it's superior in some aspects. Right. This is how, at least trying to visualize or understand what a large language model is all about. It uses generative AI, which is a very difficult task because it's unsupervised mainly. I use the transformer architecture, which is using ChatGPT. The T is for transformer architecture. The idea here is, as I said, uh, long short-term memory has this problem about decaying. So we have a mechanism to focus on some of the data, an attention mechanism, so that we don't get into that trouble. That's how the problem is solved about gradient decay. Okay, there is something here called transfer learning and fine tuning. Transfer learning, if you train a model based on a sensor, for example, but you change the sensor, technology is advancing, and you have all data. How are you going to use that all data you want? You don't want to throw it away, and you still haven't collected data with the new sensor. So you want it to reuse the old parameters, but figure out how you transfer the learning, the old learning, to the new equipments, if you like. And there is types of core tasks. We need to do some kind of normalization. The market is very big about the application of this. Trillions of dollars. That's why you hear a lot of noise, because there is money behind this. The investors are putting a lot of money, and they want to get back profit out of this investment. But let us talk a little bit about how we are going to make the assessment. We talked about alignment or evaluation or validation. So there is ethics. Most of the time I present this slide, people just ask about the ethical part and the morality and those kind of things. So there is people whose interest is just to address this. Toxicity, bias, is this machine biased to the data that we trained on, or it has generalization capabilities? Is it truthful? Is it safe? Is it risky? All those kind of things has to be defined precisely. For example, support vector machine minimize the risk, but risk is the expected value of the variance. Variance is the expected value of the deviation from the mean. So it's all about this math that we talked about in the first session. So it's not just subjectively we say this is risky, this is safe, this is not safe. We have to do number crunching to support that claim. And there is specialized large language models. There is organization to do so. We have to deal with systems that's going to receive questions from the user and answer them, UA systems. And we need mechanism to complete knowledge. If it's not complete, do reasoning and do tool learning, not better recognition. The tool itself has to be learned by machines. So this will tell you like the kind of things being done behind the scene before you see your ChatGPT or Claude or whatever machine you are using. A lot of issues that users care about. They want it to be secure. They don't want to put their face in a cloud without their permission. They want to keep part of their data private. They want to put it in the secure zone of the phone. For example, your fingerprints. You want to put it there if you like. You want to talk about authentic things. If somebody told you something and he said, "Oh, this is ChatGPT," how do you know that it's ChatGPT model? Maybe something he came up with, and he want to manipulate you. And when we talk about agents, we want to know what's the impact of trusting some of the agents or not trusting some of them to do something very serious like financial decisions, buy, sell the stocks, or even just getting a contract automatically between your agent and your service provider. There's negotiation happening and those kind of things. How do those agents talk? They don't use natural languages. They use other kind of languages, machine languages, to, to share their findings, their models. They talk in a different way than the humans. But this is one of the biggest thing right now in the machine intelligence. It's agent. You hear about the term, this is agentic AI. What does that mean, really? An agent like a human agent, now you have a machine that you trust. You told the agent, this is what I want, but I don't care how you're going to do it. So it has freedom to find resources to do whatever you ask it to do, and to build that agent for the service provider or for you in your end platform. This is your mobile or your computer or your factory. It takes a while to come up with something that's useful enough. I want to make sure that in the future, we are going to be dealing with multiple agents. Which one are you going to trust for which task? Right now, coding, computer programming is done by those agents. There is big coding agents, and some of them are specialized in image processing, some of them are specialized in finance, some of them are specialized in touch analysis. When you keep touching links while browsing, they are analyzing what you care about. And next time they are going to do suggest something for you that even might be you didn't ask for. We have to deal with stuff like ethics that I mentioned before, and risk, and logging, keep track of everything. If things went bad, we want to have a log of what happened to try to fix it or try to take legal actions or whatever. So this space is going to impact every kind of job you think about. Most of the new stuff right now in this game is happening with agents. Actually, just last year, just to give you a feel about how big this activity is and what the trends are, just look at the coding agents here, because right now this is impacting a lot of the software guys like Microsoft, Google, something like that. They say that 75% of the code is generated now by machines. How are you going to test it? How are you going to develop it and trust it? And what protocols? Because this story is getting like into standards. Even for communication, I'm using this protocol for the agent to talk with another agent, and so forth. I'm going to talk about something called retrieval augmented generation and how it ties with agentic here. There is agents dealing just with voice, other agents dealing with text, other agents dealing with videos, the agents dealing with touches. It's actually impacting even the research community. Right now, before you start working on a subject for students who are working on their master, PhD, your competition is going to be somebody else, another student who is using this to come up with a better dissertation and qualify and get a job and those kind of things. how do we, people working on the teaching industry right now, they ask students to do something, but they use machines to do their homework. How are you going to evaluate students using those tools? And some of them never even heard about the tools, and they don't even, they don't have the the ability to buy them if they are not public domain. Okay, now what we mean by retrieval augmented generation. This is different than retraining or a pre-trained model. Now, the difference is, even if you have the model, the reason is going to use additional documents in addition to the pre-trained model to produce an output. The model could be a large language model. It could be anything actually, but here, because we are talking about large language models, it's important to mention it. Use prompt engineering, which is how you are going to prompt those large language models here, for example, to get the final response. So this is the context. The additional documents could be what I care about really. Forget about this huge trillions of data points. I'm talking about this specific need. And retrieval augmented generation is really supposed to address that. But with the notion of agents right now, it's becoming agentic retrieval augmented generation. We start with a query, and we have large language model agents, and we use them. This is the kind of the one typical architecture, if you like. So I said in this session, we are focusing on the engineering more rather than the fundamental mathematical descriptions we provided in the first session about the definition of expected value and those kind of things. But it's one area that's developing very, very fast. And it's not like we say, oh, it's solved, just stick to what we get and that's it. Oh no, it's ongoing. There is online change in it. Just to give you a feel about how you compare fine-tuning versus RAG, retrieval augmented generations, there is ups and downs for each. For example, one of the weakness of one of the strengths of RAG, for example, you deal with up-to-date. Because I'm giving you my query and I'm giving you something that's I want you to take into account, which is happening recently. Report, whatever. Here, fine-tuning is actually the strength is, for example, the accuracy. There is a problem here with this strength, because what if this additional information is conflicting with some facts? That's a danger. So how are we going to deal and get the strengths and suppress the weaknesses? That's part of the design of those techniques, if you like. Okay, this is just in
عن إذنك يا دكتور.
statistical
hypothesis.
لا؟
يس ايوه معلش هاي بس لانه احنا كده طبعا انتقلنا من للسلايد سلايد 100 مشينا ل 101 فدي ذاتها this is a huge milestone. فقلت يعني ده لو سمحت نستمع للناس لو في أي ملاحظات في المرحلة دي أو أسئلة. وغطينا حاليا نقول ساعة وربع يعني. ف is that fine with you؟ تفضل لنا.
Yeah. Go ahead and ask.
Yes.
Maybe that's going to help me continue the rest of the presentation. Maybe some of the questions are going to be answered in the rest of the slides.
في البعد يا صح. Yes.
Right, but let's at least stop here.
Yes.
I'm going to skip the presentation mode to be able to see you.
All right. تفضلوا يا شباب. اوكي. وعلى ما اظن معانا شابة واحدة. اوكي. فتفضلوا لو في اي ملاحظات.
I hope this time I'm not bothering you with equations.
No, that's fine. So
I try to make the concepts visual rather than
ممكن تستوب شيرينج سكرين بعد ذاك نجي راجع لها ثاني.
Okay. Yes,
please. بعد لا بتصل السيت في السكرين موجودة.
Sorry, still. So how am I going to stop sharing? You want me to stop sharing?
Yeah, stop sharing now. وبعد ذاك نشوف. Yes, أو اختار. All right. Yes.
Because I might be.
كده كويس. Yes.
Sharing right
yes.
now.
Yes. All right. Thank you. So now the floor is open for question and answers, or if you have any comments, so please go ahead.
You know, now, Yad, I'm having trouble about sharing again. I couldn't see.
No, we'll share it. Okay.
You are going to give me permission to share. Okay.
No, it's still with you. The permission is still with you. No problem. اتفضل يا شباب. في يعني غطى الدكتور مجدي الجزء الكبير، يعني نقول فضل 1/5 من السلايدز. يعني طبعا في جزء منهم اتغطى المره اللي فاتت
They are the most important part of the presentation.
نعم.
We're going to need time to go over them.
نعم.
Not just for completion.
Yes,
yes. It's very valuable to tell you what's happening right now in the space.
نعم. في أي ملاحظات؟
And what's the future is going to be.
Yes, exactly. ده في التكملة البال يعني.
Exactly.
وطبعا ممكن نوقف التسجيل إذا برضو نعيد التسجيل. Okay.
This question is a very important part.
Okay. Yes.
Some people are going to see the record. They are not participating live. If there is nobody, you can feel free, you Yad, to ask a question, just to encourage people to ask.
نعم. اوكي. انا طبعا حقيقه عندي اسئله في المحاضره اللي فاتت. اوكي. لانه الجزئيه ديك عندها علاقه بالماث والالجوريزمز وكذا ذاتها يعني. وانت هناك في المره اللي فاتت تكلمت عن الكوشن. اوكي. which is اللي هو division of two polynomials. وبعد ذاك في الجزء اللي بعده اتكلمت عن الماتريكس ومن ضمن الميجرز اللي هو كنا بنتكلم عن اليوكليديان ال بي is equal to 2. اوكي. وبعد في اللامدا ميجر الجزء ذاك يعني. فكان بالنسبه للسيشن بتاع اليوم ده طبعا اقرب للتخصص حقنا نحن شغالين فيه بالذات انا والباشمهندس امير. فده بالنسبه لنا.
Most of today's material is you find it in textbooks. The first session you are not going to found it in a text.
نعم نعم نعم. فعشان كده مهم جدا
Right, but you are right.
انه
But
just التوضيحات
actually,
يعني.
I,
Yes.
I think I understand what you wanted to ask is the P matrix, which is B equal to like Euclidean, B equal infinity, B equal one, it's the taxi cab distance, and the new metric. I don't want to commit to any of them. We have a principle in this space, we call it the principle of least commitment. You don't want to commit to any of them. You just want the data to talk and tell you which one should be used. And that's like searching for those lambda. That's good for the machine. And is probably the machine can do a better job than humans in trying to tune that value of lambda. Okay, but the issue about the measures, not the metric, is what's the problem of probability? That's I was trying to emphasize last time. When you say the probability of not A is 1 minus the probability of A. If you plot them, this is a straight line. It's not the fact that it's linear, nonlinear. The fact is probability, excuse me, there is some people here from a statistical point of view and they don't like to hear this. But we say it doesn't differentiate between ignorance and negative information. And that's a big thing. When I say the probability is going to rain is 90%, is not going to rain, has to be 10%. We don't want that restriction. We want to say the certainty is going to rain could be 70, not going to be raining is 60. What's important is consistency. When one of them increases, the other shouldn't. And that's a monotonicity requirement for measure theory. I think this topic is like a big thing. I don't want to waste a lot of time on it, but it's what we learn. It's like when you force the confidence for H and B to add to one, you can read one word and misread the other just because the confidence of H and B add to one, and it's exactly the same better. That's how I write my H is exactly how I write my B. I hope at least I give you a reason to rethink it. If you don't see this is,
Yes.
I was talking about precise probabilities. There was something called imprecise probability, that is very difficult to formulate. So this is just an attempt to formulate it.
نعم نعم. سمحت تفضلوا يا شباب يعني نعم يعني انا بالنسبه لي كنت شكرا على التوضيح وكده. وانا ممكن كان امشي في الجزئيه بتاعت السوبرفايز اند سوبرفايز كلاسيفيكيشن والسيجمنتيشن وكده، وحتى الايمج اللي انت وضحته from data to knowledge up to wisdom. اوكي، والجراف ده جزء بتاع الفيجواليزيشن برضه يعني. ولانه تداخل العلوم هي yes go ahead.
It's just a cartoon representation to convey the concept. But how we do it is with numbers. And that's what's going to be my next slides. How are we going to accomplish that? By that ugly math we talked about is not there is no one way to do it, because we are talking about stochastic processing here. We are not talking about deterministic task. I have data, sort it, numbers, sort them. That's deterministic. I have a dictionary, search if this word is inside the dictionary or not. That is deterministic. We are talking about non-deterministic or stochastic processing, if you want. So I'm going to share
Yes,
that
please.
to
Okay,
make
yes, yes, please, yes. إذا ما في سؤال يا شباب احنا حنمشي للجزء عشان يكمل لغاية السلايد الأخير
I
بعد
can take
الثاني.
the questions
Yes.
after
لا,
after
for sure, yes.
addressing
So,
those
so go
kind of
ahead.
things.
Thank you. Sure.
So I'm sharing now. Okay. Slide 101. Can you see it?
نعم. Yes.
Let me
تفضل.
put it in presentation. So statisticians talk about type 1 and type 2. What we show here is called the confusion matrix. When something is true, the machine rejects it or accepts it, or when it's false and it's being accepted or rejected. That's what we talk about here in type 1. This is type 1. This is type 2. We want this error ideally to be 0 here and there. And here it's in the diagonal arc, it has to be high enough. So this is the mechanism we are going to use to define formulas. How we are going to quantify this thing, which I have an actual class and have a prediction. Positive, negative, positive, negative. So this is a terminology. When a positive call positive, we call it true positive. When when a negative call positive, we call it false positive or false alarm. When you hear about this term, that's what it means. And by the way, this is just for a threshold. It's not for the whole machine yet. We are going to show how we are going to do it for the whole machine. And when something negative, we call it negative, that's good. We call it true negative. So true positive and true negative has to be very high to say this machine is better. And sometimes we might not care about false positive and false negative the same way. For example, if somebody has cancer and you tell them you don't have cancer, is less serious than if he has cancer and you tell them you don't have cancer. So depending on the application in health and whatever, we look at those with different from a different point of view. When we talk about accuracy, that's what it is. This box, we add them, we normalize by the full. Precision is this box when we normalize here with true positive, true. Just the fact that we normalize row-wise or column-wise give us a different index. It's all about something called the F score. 2 divided by 1 divided by the precision, 1 divided by, specificity is defined by true negative divided by true negative by, I know this might sound very weird to most people who are not in the game or in statistics in general or decision making, but this is how we are going to turn things into number. Okay, we just keep counting, generating those confusion matrices for every threshold, and we compute those numbers. Okay, now we are going to use all of them for every decision, and we build this curve called receiver operating characteristics. So if I have data which is normal, but it's overlapping, so if the data is separable, those distributions will not be intersecting. So you will just have true positive, true negative, the ideal thing. False positive, false negative are going to be 0. And visually, that's the blue bar. I'm trying to use color here to just turn the ugly mass into something that we can visualize. This is the true positive things. This is the true negative. And this is the threshold for just the 2-class problem, 0 or 1, true or false. So when we plot it for each possible threshold, we get a curve. If the machine doesn't have any skill, this curve is going to be like that. But if it's very good, this curve is going to be high here. If I have two algorithms, that's one of them has the curve above this, I'm going to stick with it. That's mean this is a better thing. When somebody tell me that my machine is better than you, he has to show me this thing. When I'm trying to see how good my algorithm I'm building is getting every time, you have to look at this from every point of view for every possible threshold. Finally, when I pick the right curve, which is the right machine, then I need to pick the threshold. And that's what's going to be running in the machine to call things 0 or 1. Okay, here I'm just summarizing the terms I talked about in the previous sessions. What do people mean by saying artificial intelligence or computational intelligence, as I like? What's machine learning, which how we build those models? What's deep learning, how we are going to use them for autonomous cars, for Tesla, for example? What we mean by generative, which is the density estimator part, not the discriminant neural networks. What's retrieval augmented generation? I'm just trying to visualize to you the concept that's being described. What's AI agents, agentic AI? What's generative AI? It's all about how we structure things, how we architecture the system. In terms of communication, there is model context protocol because we want those machines to talk to each other. So there is standards in how we do that, how Google Drive is going to talk to GitHub or whatever is by those protocols, if you like. Very quickly, I slightly mentioned in the previous presentation the term prompting. What do we mean really by prompt engineering? Okay, which been used inside those architectures. Okay, we start with user, we generate a prompt for the machine. There's some design about how we instruct it. They have to give some examples and so forth. So prompt engineering is just trying to model or to represent how the human is going to, or even a machine actually is going to express the need. But when we talk about context engineering, now we have another part, which is called the context, which could be the additional documents, for example, those kind of things. How are we going to incorporate it into this story? Is also something very interesting for people who want to study those kind of things or change what's happening in their model by default. Right now, this story extended to something called harness engineering. I didn't prepare a slide on it, but this is like the big thing in the game is what's called. So this is going to generate new jobs, new tasks to be done, a new development. The competition between those competitors right now is in this harnessing engineering. To give you a feel about what's the harness engineering is about doing the intelligence not just for the model, even if we fix the model, just the resources around it. Which API should I use for generating this code? Which security measure should I imply because of the sensitivity of this application? So we are doing intelligence, it's system engineering, if you like. And that's very, very interesting aspect. So from going from prompt engineering, context engineering, and right now, harness engineering is a big area. I'm not going to read this because I didn't put enough information. I thought I should leave it if somebody wanted to study it more carefully and see how it fits in those models, RAG or whatever, to see what's. This is a different kind. I am in slide 108, Jad. If you can hear me.
Yes,
Slide
yeah, which is the
108.
diffusion
Right.
model. Yes, yes.
This is very important to what we call right now generative models. When we generate new images, new medicine, if you like, new biological weapons or chemical weapons for the military guys. This is the latest thing that's being are delving into. So the diffusion model it does things differently. It's not doing it from what we call autoregressive point of view. It's from a very different kind of things. Is you have data like images. You keep adding noise to it, for example. I'm just going to show you how we use it for generating new images. But you can use it, Adil, for example, for generating new music, which is happening right now. The songs that you hear generated by AI is using these tricks at the level of phonemes or something like that. And you keep adding more noise levels to this input in the forward direction. In the backward direction, you do the opposite. You denoise the data. You try to clean it. In that process, you figure out a model that's going to be like your distribution. And from that distribution, you can generate the synthesized data. I hope Imad is here too, because he asked me last time about what's the importance of synthesized data, how we gonna deal with it, and I provide some answers to that. But this is a different kind of uh, uh, of modeling, constructing modeling that are very helpful right now for the fields in the like health, like art, and even in science. We can right now talk about generating new molecules. Moreover, we can generate materials, whether it's biomaterial or just plastic, or we can generate new things with those tools. This is a tool for the people who are designing material, designing anything, you name it, because it's done at the lowest mathematical level. That's what's the beauty of math. If you solve it, if you solve the mathematical challenges about noising, denoising, then you can apply it to different domains. This is one of the use cases which is really, I was surprised. They have a paper that I published in some time ago, 2010, and I just received an email from something called academia. It's an organization, and they generated this podcast for one of my papers. The paper actually talks about 5-year work for a PhD students of mine in UIC. And it's impressive how they summarize that paper in a 5-minute video. The paper talks about decentralized, you mentioned, as I mentioned before, multiple camera, multiple object tracking. And it shows that system using AI, of course, particle filters particularly. And it's just a different kind of filter. In 5 minutes, summarize 5 years long research. Here I'm just showing that a snapshot of the output of that solution using 2 cameras in Chicago Union Station, tracking multiple objects, and there is serious occlusion. But from one side, it's occluded, from the other side, it's maybe partially occluded, but both of them, when they work in unison, the accuracy went up significantly in terms of all those indices I talked about before. So it's for N cameras, actually. And if some of them stopped working, the system is still working, because we did a lot of work for the formulation of the algorithm itself to work with multiple input, and how we do something like how we synchronize the data. Look at just left and right camera, the impact of light on this frame. Here it looks lighter than this one, but it's the same algorithm running here and there. That's why we do normalization for the inputs before we push it into the model, because the model is going to be challenging if I just showed the input as is. So we change the input. It's not just the machine agents that are going to be talking to each other. It's the machine agents and the human agent, if you adopted one, and the people, the humans in the field. So when we do landmine detection, there is a human behind the loop. How to orchestrate all those kind of things it depends on the application. And there is no, like you said, this is a golden way of doing this job. There is a lot of engineering and it's slight change. That's why this harness engineering is the big thing right now. How we are going to harness, how are we going to make those elements fuse, if you like, and give me a better output. I'm close to end yet. Here I thought, because I couldn't go over all those use cases that I did myself. For landmine detection, how are we going to use a ground penetrating radar imager to detect if a buried landmine exists or it's just a rock or something like that. Sewage pipe inspection, we put a robot inside the sewage pipe because we cannot put a human. It's not just we are trying to say, okay, we are replacing the human. No human can be there in that environment. It's sewage pipe. So we need to use robotics and determine, for example, the sewage pipe, because that's where road collapse. For safety, we need those systems. It doesn't have to be real time like landmine detection, but at least we want it to get fast enough before the road collapse. Material design, I talked about it slightly, but there is a video about it. If you Google this term, diffusion models, you will see very interesting videos. Text to multimedia is the paper, converting a paper into a podcast. In the future, I would expect flowchart to code. Actually, have a patent on this subject. Just show me your flowchart drawn by your hand, take an image of it, the machine can generate the code for you. Not just from a textual description of the task, even from a flowchart. Right. But you have to tell me what resources you trust more. If you want to use certain libraries, I have to have access to those libraries. but I need to understand the flowchart. That's very difficult for the machine. This is computer vision task, but the utility is generating code. Gesture recognition, I have something like, let the user define his own gestures and give them labels like stars is one alphabet, moon is another alphabet, sequence of them is my alphabet. If I did it this way, and even if you know my alphabets, you cannot, for example, use it as a pin number to open my phone because the way I draw the star is different than you. And this is turned out to be more accurate than fingerprint recognition. I talked to you, Yad, about hyperspectral imagers. Now, what we are using for machine vision or computational vision is actually color sensor, RGB. But for hyperspectral, we expand the bandwidth. Red, blue, green, infrared, and beyond, up to like 12 wavelengths or something like that. Why are we doing that? Are we just trying to complicate the problem? No. We wanted to detect materials. Even I can tell the difference between a green t-shirt and a green grass with hyperspectral imaging. So what I'm trying to say, the advantages are coming from a lot of fields in the imaging, in the sensor technology, in the AI technology. So they are just trying to make use of the best sensor, the best model, and the best way to combine them to build a better system using, for example, this harness engineering. That's how we design things right now is totally different than how we used to do it. Broker phone, this is something my agent is talking to internet service provider to find a better deal. And I don't even know, I just allowed my agent to do this and get me a better deal, getting a better contract. Student tutoring is using large language model is also a very interesting field. Distributive collaborative communication, when our multiple people are working to solve one problem. So there is tools using AI to do that. Last time I mentioned the smart power amplifier, how we design, why that's intelligent, why we couldn't do it before this machine learning capabilities are available to us. This is first responders. People work with the police departments. There is some intelligent machines to help. This is just a title of one of my patents, actually, signal processing network and genetic computing method of designing the same. I mentioned genetic computing, but right now, a lot of activities is using AI to do gene expression programming with hidden Markov model, or to improve hidden Markov model with gene expression program. Sometimes we do it in the reverse manner, depending on what problem we want to solve. It's all about aggregation. How we combine those pieces to build a better machine. That's where intelligence is. Super smart agents, this is an endless story. How we make agents that every time they are even learning by themselves without I teach them or I give them data. They have access to other information that I might not have access to, and they are getting more. I'm going to talk about the future slightly because it's bounded by your imagination. Nobody knows exactly what's going to happen tomorrow or next week, and this game is changing rapidly. But at least I can mention something in the field of AI, robotics. We want them to be better, but better with respect to what? It's more important to try to quantize your goal than how to optimize it. That's a different area for those industry engineers to figure out a linear program or something like that. But sometimes most of the research is what should be the objective function? Should I try to maximize entropy or minimize the differences between the target and the output and those kind of things? Well, as it's as I said, it's bounded by your imagination. This is what Albert Einstein says: imagination is more important than knowledge, and we keep talking about knowledge, 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 but it's really driven what is function of how we are imagining. That's why it's tough, because right now we are trying to imagine what's happening in that high dimensional space. People in space technologies it depends on the sensor technology that's make their theories and whatever they develop based on what they can observe, and visualization is very important. There's going to be a great degree of interrelations among, I should say, most of those technologies. The intelligent device, the next generation cloud, where routers are supposed to be smart routers, neural network that's going to have better capabilities in terms of dealing the number crunching, or in terms of getting robust behavior, in terms of getting interpretable structures that has meaning to the user, not to the developer only. Battery design is going to be using a lot of those tools. That's why somebody like Elon Musk is investing a lot in this game. It's just because of the battery. It's just the core thing for this electric vehicles, if you like, and the autonomy. While you want to be driverless car or something like that, is also interacting with what kind of batteries we have, what kind of neural network. People in the health space, health services, talk about precision therapy. That could tie to something like a 3D printing. If you want to customize drugs for me, just me, depending on my data, then it's going to be 3D printed when you go to the pharmacy. That's where people are envisioning what's going to happen in the future. It's not happening yet to the degree or the cost level, if you like, to be mainstream. And everything is turning into computation. Computational biology, computational chemistry, computational physics, computational political science. So don't think that this field is not going to touch you because you are in a different space. No, it's going to touch you. Let us see, just for example, I'm going to show you how it's impacting health and heart rate. This is just a comparison to show you what's happening by the machine alone, the green, the machine and a human cardiologist, and the cardiologist alone. And just look at those three terms that we defined before: accuracy, sensitivity, specificity. That's what doctors cares about. Look at, in this case, the fusion of the human and the machine didn't help. It actually hurt the machine. Just doing it. This doesn't mean that's every problem in health, that's what's going to happen. But in this specific task, this is what's happening. So that's a good incentive for doctors to try to use those tools and see if it's helping them or not, than just working without the machine. And if they trust the machine, maybe they can tell the user, sometimes go ahead and use this machine before you come to me, and I'm going to double check it with my classical or in my lab. I need to design a better way to help you be better. So that's in health. There's some people who care about blockchain and what's the future of currency is going to be done. Most of those tasks are done with machine learning, right? So understanding how that technology is consuming intelligence is very important. It's going to impact our future, whether we like it or we don't like it. It's going to impact it. And even the research, right? When you start for students who want to start new subject, not even doing research, just going to university. Those are tools that's available to everybody. Right now, most of the universities are talking about distance learning and those kind of things. So that's a use case for the academic uh, kind of work to be done. What happened, just this is a visualization to show you that what happened by DeepSeek, this company, which is still small relative to it, what happened to NVIDIA is like what Apple did to Canon in 2015. That's happened in 2025. So you expect big surprises in this game to the big corporate, the big banks, and the big service providers and everybody. Okay, processing. I talked about parallel algorithms slightly. What's the difference between concurrent computing and parallel computing as part of my interest, actually. But here, this is just also descriptions to tell you we mean by concurrent, not parallel, concurrent, not concurrent, and not parallel, parallel, concurrent, and those how those data centers are partitioning the task. Sometimes because of the nature of what they are doing, sometimes because of just some hardware available to them and they wanted to you utilize it to solve the problem quickly. That's what's the initial definition for intelligence. So to do it fast, it touched on quantum computing because there is big promise if when we build those machines and make them available to the end user, they are going to do things very fast. And that's going to help both the encoder and the decoder part of your system, if you like. So there is a two-way things. How quantum is going to help intelligence is because of the promise of the speed, but intelligence is also helping quantum to figure out better designs. So it's the activities goes both way in most of what I mentioned before. So there is people who are from physics point of view, they wanted to, to understand what's happening in quantum physics compared to relativity, Einstein, and gravitation, and those kind of things. And AI could be helping them to find those links, if you like, the interrelation between what's happening. And probably what's going to be the next big theory in this space. Well, I am close to end, but I selected some of the quotes that's being said in this regard. And as I mentioned before, even the definition for intelligence changed from solving the problem quickly. Now the issue is it's not just solving the problem quickly, because we have quick machines. It's about thinking fast. Is just about having actually a more consistent, whether it's the machine, it's a planet, or something like that. We want it to be better in a lot of regards. So in this game, precision, I hear you, Jad. This is a slide 124. Can you hear me?
Yes,
No.
yes, you are at the selected quotes. Yes,
Right.
I do hear you. Thank you.
This is something hard to believe. In this game, precision does not imply intelligence. It's how you deal with noise. If you become very precise, you are going to outfit. You're going to fit the noise, not the real useful data. Is risk really the expected value of variances as we defined it in most of those models? Risk is more than that, because we can incorporate a lot of other things inside the equation, if you like, of quantifying that quantifies risk. The name of the game for generative, they say, what I cannot create, I cannot understand. If you cannot create blood, you don't understand blood. Until we reach the point that we can generate blood, we can claim that we understand it. Some people might not like these things, but I love it. And we need to understand the pieces so that we can cultivate the best out of those technologies. Okay, this statement is said by Vapnik. It's a Russian scientist who invented support vector machine, because people used to argue with him and say, oh, this is a beautiful math, but sorry, I have a practical problem that I want to solve. And his response is, nothing is more practical than a good theory. Because if it's a good theory, it has to be practical. If it's practical, it has to be built on top of a good theory. That's what he's trying to say. Intelligence doesn't have polarity. You can use it to do good things or bad things. So we have to guard against that. That's why we care about ethics, we care about morality, those kind of things, because there is people who are going, we need to build safeguards. There is people is going to use this agentic technique to do agentic hacking. How are we going to minimize or prevent that, or even recover after it happens? That requires more sophisticated. It's interestingly, people used to think that if you have a machine that has more parameters, it's more intelligent. And Vapnik said not necessarily. You could have a machine with less parameters that's more. And he defined something numeric called the VC dimension. That's why math is helpful, because math is very precise. Although we talk that precision is in the data, but the math is, when you say this machine is better, it has to be in some respect. No, you cannot say vector 1 is better than vector 2 in high dimensional space. All you can say is they are different, belong to the different clusters, but you cannot compare vectors as a one-dimensional thing and you sort them. You cannot sort vectors. You can only cluster them, or at least you can cluster them if you like. So my best quote is actually come from an advertisement for a tea brand. It's saying, with the freedom to choose comes the obligation to choose right. Now I gave you a lot of models, a lot of parameters that you are obligated to use or find the right one. Okay, and the only limit to our realization of tomorrow is actually is our doubts of today. You have to question our machines. Don't take them for granted. We have to doubt. That's why we argue with even what we make ourselves to be able to get a better machine. Most people ask me, they say, oh, is AI going to take my job? I try to answer this question with the cartoon. It's not AI that's or machine intelligence that's going to take your job. It's somebody else who knows how to use that machine. He's going to take your job. So that's my last question. My last slide, and I would be more than glad to answer questions. Yeah. Should I stop sharing or continue?
Yes, please stop sharing, and then perhaps we might ask you again to put some of those slides. Thank you. تفضل بروفيسور سامي الشريف. شكرا، تفضل.
مرحبا يا دكتور.
مرحبا بروفيسور سامي. It's good to hear your voice. Long time.
الحمد لله. كيف حالك؟ أنا استفدت كثير جدا من السلايدز والمحاضرة دي والسابقة، وقد تشكل بعض الأفكار اللي قد تكون خطيرة، يعني ما عندها رجلين، لكن هي الحياة تبتدي كده. فمن بدري أنا قاعد أفكر إنه في الحتة بتاعت الريكوجنيشن دي في a lot of uncertainty، موجودة عوامل كثيرة ما محددة، فلا تحد ممكن نستفيد من الكوانتم ميكانيكس to improve الماركوف موديل، هيدين موديل، أو البروبابيليتي ثيوري التقليدية المستخدمينها نحن في الشغل بتاع التعرف، وسواء كان الشكل بتاع التعرف. أنا ما عندي ديفنس فور ذيس قضية، لكن كده في خاطر بتيجي في بالي، فيمكن يكون في improvement كتير لو حولنا من البروبابيليتي ثيوري للمالتي دايمنشنال والانسرتينتي بتاع كل حاجة. It is area for thinking، أكتر من إنه حقيقة أقدر أقولها. معليش الأفكار مرات بتجي كده.
I think I got your point, and I'm very happy that you use the term uncertainty. I'm talking English because some of the audience don't understand Arabic. Even our kids actually don't understand Arabic. So I'm going to answer it in English with your permission. So,
لا مرحبا.
Right, it's uncertainty is the core of what we are dealing with. Probability theory is just one way to deal with your uncertainty.
That's true.
It's one way, it's not the only way, it's not the best way. Right? So I opened the area to say there is more than a probability additive measure. There is something that's I call, you measure, other people use it as belief plausibility measures, and there is some state of mind that you cannot characterize with probability. It just whether you accept the new one or not, you have to admit that probability is not going to solve this problem. You have to, this is the first step. Then you explore what's available. If you get better results, well and good. And that's why in the hidden Markov model, for example, you mentioned, I generalized it. I said, I'm going to search for you even the measure. But if the best measure is probability, the model should tell me that your lambda should be 0. I didn't impose it. I just made it an option for the machine to figure out. So that's great flexibility, and it's fair. It's a fair game. Actually, my code base is the same code. If I just fix lambda, I'm getting the classical hidden Markov model. If I let it go, I could get something, I call it plausibility, or I call it possibility hidden Markov models. This is one part of your question. It's just something that's very hard to be done with the classical things. Now I'm just using a different tool to make it better. I shouldn't be worried about that. I should be worried if I stuck with the same classical formulation that took 400 years to be accepted as a mathematical science. Probability. This is the first part. So we have better tools we need to explore. But you have to understand what the tool is capable of to be able to generate the right prompting for it, to be able to design a better solution, whether it's a device, it's a process, whatever. That's the first part of your question, which is it's just how we deal with ambiguous situation. It's not randomness. Total difference between randomness and vagueness in this space. Randomness can be characterized by probability, but vagueness is more difficult than randomness, even for signal processing. Right now, if I don't know that there is reflections to my signal coming, every time I repeat it, it's the same thing. So if I couldn't solve it the first time with reflections, I'm not going to be able to use it with randomness model built around randomness like probability. The second part of your question is quantum. As I said before, the story is both ways. Quantum processing, this is going to be like a new hardware. You have your CPU, your GPU, your DSP in your phone, for example, like Qualcomm chipset is actually 3 parts like that. In the future, you are going to have those pieces when they are small enough to fit into those chips. So it's a different platform. The promise is going to be extremely fast. Okay, that's good because I need fast is good for me because that's how initially we define intelligence to be solving the problem fast. But as I mentioned before, it's more than that. It's more than fast. You want it, the solution that's going to sustain, is going to fix itself. It's going to have online learning mechanism, and that's going to having while I'm using it. So quantum can help in that respect. Quantum can help in communication. Those entanglements, I try to avoid using the terminology in a totally different field. I don't want to confuse people, but they promise communication is going to having with zero latency. Because you could exist in 2 different places with probabilities. Unfortunately, they are still using classical probability to do formulation. But I'm well to accept it because I am not in the game. I'm going to accept it even with probabilistic thinking. But if you talk to people who like Einstein criticized probability, as you know, significantly by saying God does not play dice or those kind of things. He has concerns about probabilities. But no matter what, let us solve it with probability. Then we know how to extend it to the new measures. So AI can help in that regard. Right now, in something like string theory, which people use a lot in physics, or they are not, it's just like a new game. They say, okay, we are dealing with 10 dimensions. Why 10? They went to 20, they came back to 10. they need tools to really make that string theory based on a very solid foundation, for example. So as I said, the role, how this going to interact, the relationship between quantum and AI, this is going to be both ways. Every field is going to benefit the other field, depending on your strengths, where you feel you can contribute to. Probably that's where you're going to consume most of your effort. But I wish that we invite somebody from that background to tell us what's the state of the art in quantum algorithms, quantum physics, and so forth, so that we understand the limitations, at least, of why is it very big thing in terms of physical size, those machines. And the great thing about math, as I always look at it, if you look to this guy, Vabnik, he talked about the dimensionality, and he said, I am going to give you a tool, and that's in 1960, that's going to reason in an infinite dimension space. So the demo I showed last time is working in infinite dimension space mathematics. That's very intriguing. And he saw it in the math. And we are still struggling to deploy it in machines. Some people would say, oh, I tried support vector machine, it didn't work. He didn't know that he picked the wrong parameters. And that's why I tried to show, if you change this parameter, this is what's going to change. He gave you a flexible mechanism to think in infinite dimensions. Right. That time in 1960, he couldn't realize it. It was realized very recent, like 20 years or so. And it's still a very big thing. So I hope that at least I addressed parts of your questions. I mean, it's a huge question. It really just need like one complete presentation to answer that question.
Yes, as I said, I'm not. It isn't. I think you know there is a problem, or at least for me. Probability is designed and developed for a random Scottish process.
Correct.
And what we are doing with is not a random process. Yani every twin or every
right, incomplete dig, right,
related, and some features of that quantum mechanics theory. So how we bridge this gap? What is the assumption we are used for this probability theory as a theory for random chaotic process, and to apply it here? How does that affect our results?
It's going to.
I'm just thinking. I'm not questioning. Please.
Oh, right. Yeah, it's a good question. You should question it.
Yeah. So that is what I have
to argue about it. Actually, right. So let me just give you a glitch of what's in my mind right now when you expressed it, or you prompt me with a different statement. So I start questioning probability. I said it's an additive measure in the sense of setting inclusion. But if you really pay attention of what I did in the Q measure and the Q filter story, I kind of reconciled with probability in a different space. I said, oh, I don't want probability to add to 1 because I don't want probability of A is equal 1 minus probability of not A. It's not going to capture what I did. But if you look at the number crunching happening, the difference between those Q measures as weights for the filter, they actually add to 1, and they are number between 0 and 1. So I kind of reconcile, but in a different space with probability theory. But the beauty is, at every moment, I am using non-stationary distribution in the fly. Okay? So that you make the analogy between what's the probability distribution or not. So I'm still seeing the differences of weights as probabilities, but from a different distribution. And that's how we cope with the change in the dynamical systems. Is that being captured in the classical quantum formulation? I don't think so. But let us just start with the static situation. Just solve it there. Then we can bring those non-stationary distribution in the game, if I understand your concern fully. But if right now I have this mechanism available to me in hidden Markov model in a neural network, why shouldn't I use it and wait for the quantum machine to come? Right? I shouldn't wait. So it's all about stationary versus non-stationary. That's how we are going to adapt to new environment we have not seen before. We want to analyze data coming from the space, from the moon, something from a different environment. Like I mentioned before, we develop models in our labs with sandboxes data. The quality is lab quality. We are going to be confronted with different things. And what I presented is actually an option, but we are obligated to figure out how to build it, how to do the parameter estimation correctly.
عن إذنك يا دكتور مجدي، خلينا أنا أعلق أو أسألك أو أطلب منك توضح بعض الحاجات. أوكي. أنا يعني بأمانة شديدة جدا أنا استمتعت بالمحاضرتين دول مع بعض. أوكي. وتابعتهم بشكل ممكن يكون relatively good. ده يعني عن المتابعه يعني. فمن الحاجات اللي I really enjoyed it. اوكي، في انك انت في السلايد رقم 10 واللي هو فيها انت مشيت معلش انا بتكلم بالعربي والانجليزي مع بعض يعني.
This is the first session يا كريم. Your question about
yes، ما هو ده البيز اللي انت طلعت منه يعني، اللي هو بين it's a measure exactly page 10. اوكي، وحنيجي لغايه ما نصل للجزء بتاع الويزدم ده وكده يعني.
اوكي.
اللي هو في الهوريزونتال اكسس عندك البيليفابيليتي، then the probability, then the plausibility. وكلها سميتها تحت الميجر confidence of quantifier.
يا جادو, it's not just they give it a name. I'm trying to speak in English.
I'm speaking about the axis.
I'm expressing all of them in one formula.
Yeah, that is the axis. I'm talking about the axis. Okay, and then the different.
Right. So this is just a visualization.
The visualization, exactly. Yes, exactly. That's what exactly I mean. Okay, and along the vertical axis.
You want me to share this slide?
Yes, please share it.
You should share it. If you want.
Yeah, we will share it. Yeah, but at least I'm trying to pinpoint that.
Okay.
The usefulness of your contribution. from a mathematical point of view. I feel الكونتريبيوشن حقك هو في الاريا ممكن يكون in mathematical terms اوضح من الحتات الثانيه. That's my my own conclusion.
It's the other way around, yeah. It's this thinking is triggered by applications.
Yeah, but you came back.
The application that's created
that. Exactly. Okay. So now, because when we refer to
right, but then we try to share and speak in English because of the audience.
Oh, that's fine. That's fine. That's fine. That's fine. Okay. Yeah. So what I want you to show.
Right.
The slide number 10, okay, and then I want you to comment on it, okay, and then the second part, which is about the Q measure, okay, and the axioms, because in this what it is, it's page 11, okay, and where you actually spoke about the fuzzy measures and the axioms
that has been used. Sharing now?
Yeah, yes, exactly. That is exactly okay. And then here you went to the probability measure, and that is this Japanese that using the lambda measure. So those works are actually from 1933 to 1975 as theoretical. Theoretical aspects.
What I did in 2003.
And then you did in 2003. Okay, that you put it into this it's a Q measure, which is actually polynomial. So that's very nice.
In lambda, polynomial in lambda, it's a rational function.
Yes, exactly. And you have constrained. You have constrained lambda to start from minus 1, which is generally in other mathematical terms. Sometimes
it's not just I put it because I like it. I put it slowly in that frame.
That's very interesting. Thank you. So
right, but yeah, what I wanted to highlight here, I have to argue with the godfather of fuzzy logic. And he was the reviewer of my paper, by the way.
Oh, okay. Who's the one that
argue with the big guys? I don't just took their word for, and I said, it's unique. That's good. Your lambda is unique. Is good, but it's not solving my problem.
Yes,
that's like the argument I put in that paper. I said, we want the flexibility. And guess what? Your unique lambda is just one of my values for lambda.
It's for the general formula, then that's reducible.
Yes. Here I put lambda not equal to 0 because if you substituted 0, you could get 0 divided.
Because it's an infinity part.
Yes. Lambda equals 0 because this is not the way I'm going to compute. When I compute it, I can compute it with 0. In the recursive formulation. But what's interesting is actually this convergence. So this is the ugly math.
This is very interesting. Yes.
But it makes it more trustable for the scientific community to listen to me.
And if you go to page 12, go to the next one.
If I don't have those theorems, nobody's going to pay any attention to it. So he's not going to use it.
Yes, sure. Go to page 12, please, so that I make another comment. Okay.
Now we went back to session 1, but it's
good. Because that is a key, because that is what you use from math term to actually treat the probability part, and then this issue of uncertainty, because it's part of an assumption in the statistics terms that they're using Gaussian model. Okay,
that's what I wanted,
and that is what you want to highlight. Okay,
Sami, like, we're not ignoring this red curve. is just one of an infinite number of curves.
Yes, okay. So thank you for that. Okay. Now let me go forward. Yeah, that's okay. Please let me go to
the thing that I wanted to show with this plot is actually when I tell you that my certainty in A is alpha divided by rho here, according to this number.
Yes, okay. And that is
the answer to what is your certainty in not A. You know what's the best answer? I don't know. Because not A is a totally different event that you don't want it to infer it from 1 minus X.
Yes,
that's not going to capture the ambiguities I'm dealing with. So here I'm saying you are obligated to find, even Sogano's model is going to tell me the certainty of not A, because it's going to be just one of those curves.
Yeah, but because it's drivable, yeah?
You are obligated to find the golden one to answer the question, what's your certainty on not A?
Okay, very good. Thank you. So now if you go to page 38, okay, which is
I hope that I express it in terms of sentences and in terms of plots clearly.
No, 100% is clear. Yes.
Paradigm, if you like.
Okay, so
yeah, right.
Very good. So let us go to page 38. Okay.
38.
Yes.
Let me slide. 38 is this.
Yes, yeah. So the conventional, and then you kind of to the left is the regression model.
The distance,
the Euclidean distance, because all those measures, starting from the average and weights and something like that, when you go to the right hand side, this classification part, because of what they impose on the weight, the Wij, and that function, and this summation, those weights determines the other measures. Yeah. Okay. So
actually, in this slide, I was trying to highlight just the impact of the distance function. I kept everything. We're not talking about measure here. We are talking about metrics. The metrics D.
Yeah, because yes, I understand. Because yes,
but I'm saying the conventional machine is P equal to distance, the Euclidean distance in high dimensional space. And I'm trying to say that's dangerous to commit to one distance from.
Yeah, okay. That's
just
interesting.
To show you the impact of the metric, right? And it's expensive. I need to take the exponent of minus x. In my formulations, there is no exponential, there is no sine, there is no cosine, there is no Mahalanobis distance. It's just add, multiply, divide. I built it from the core computing elements, if you like, of your processor. Because my background is actually in electronics, so I know how we do those kind of things in the computer. It's add, multiply, divide, or a lookup table. So why should I use an expensive function? That's one thing. Why should I commit to just one distance function if I can explore the metric space, which is between minus lambda, between minus
yes,
yes.
And now would you please go to...
people are not going to listen to me unless I show them not just the formulation, unless I show them the use case. And that's what I should do every time I came up with a different formulations, how to train out. You show, okay, this is a classical network. This is an RBF, a QRBF network. Look at the confusion matrix.
Yeah. Okay. So, yes, exactly. So
this is a regression case. Look at the RMS for the new solution and for the classical solution. Because I was able to explore the space of lambda. Not because it's magic. It's just I did the optimization for that flexibility term, if you like. I gave you a knob to move. You are obligated to turn it to the right direction and right position.
Yes, thank you. Now let us go to.
And that's what machine learning is all about.
Go to 81.
Oh, good. Now we are in the second session.
Yeah, we are going to step by step. Yeah, go to 81.
Okay. Yes. I think you like this.
No, I like it. Yeah,
but honestly, this is just a cartoon. There is no science.
No. There is real. Here's a situation, okay? Because from a classification point of view, that is the reason I went back to argue when you showed the regression to the left and the classification part. And now I'm coming to the classification because there are multiple applications when it comes to this part, which is now so from the right to the right side of it. You started with the raw data, and then you formed the information, and then you collected those nodes. That's what we call them. Okay, that you calculate knowledge, and then you went to the lower part of it. You got the insight, okay, and then here you got the experience part. This experience part sometimes in the unsupervised classification, the machine is doing it, whereas in the supervised classification, this is done by the expert. So I'm glad you did that, and then you went further to the last part, which is now this is the creativity part, which is
how we are going to generate
new material and new knowledge. In fact, and that
I was just trying here, to give a visualization of the story. The coming slides are trying to move from here to there.
And that is why it is very interesting.
New material. How we are going to create new music, because people don't believe it. Don't believe that we can create music by machines.
Okay,
it's happening right now in front of you. I can run to you something of what's called songs being sung by AI now.
So let us go to 86 now.
Because that's happening because we give it the building blocks, the phonemes, if you like, of that singer. And it's reasoning in that space. And it's figuring out clusters of how things group. And by the way, Professor Sami understands even in digital communication right now, my speech is not the original speech that I captured here. We do vector quantization based on huge data, and we send a code vector, which is like a cluster center, to render my voice to you. So it's not the real thing, but it's useful. You can tell this is Sami's talking, this is Jad talking, this is Magdis talking, right?
Yes.
But it's done in that high dimensional space, even using the old technology without AI. We didn't call it AI that time.
That time, yes. And then Dr. Magdi, if you go to 86.
Okay, we are moving. That's good.
Yeah. So then, and here you start by classification, okay, and supervised learning, and then you use the linear to get the regression part, and then the clustering part, and there is heavy. Yes, this is very Yeah, and then going back to the last one, the machine learning.
Yes.
Go ahead.
Examples to show the concepts. It's not like I need to go from this to this to this. No, it's trying to describe to you what's the story. If you want a linear fit, you could ask for a nonlinear fit, and it will give you a different fit for the regression. You could be dealing with more than two classes. It's not just true or false.
Yes, exactly.
Right.
But it's a segmentation.
Instead of 3, you could ask the machine to cluster it into 100 code.
Exactly. Yes. And
that's what's the digit is a 10 is 100 clusters, 10 by 10 map. And each one of them is this cluster center. The weights from all the data to this node is shown as an image. So I'm showing to you all my data here, but it's in a very nice way. Showing the ambiguity that Sam was talking about. It's not randomness. People don't try it randomly. It's just my style is different than your style when I write. For example, you write it differently than me. But when we give it to the machine, we give it the whole pool of data. And we want it to know even if there is bad data or not. We want to visualize, and we want to help the neural networks to address the rejection, which is to say, I don't know. When I give it 10, I ask, which digit is that? I want my neural net to say, I don't know. Because you know what? When it passes this step, it's going to give me zeros all over this space. So the machine can say, sorry, I cannot read this digit. Meaning it's not a digit. It can reject. How are you going to do that with the classical models?
So thank you for this wonderful presentation, and our discussion with you will continue. So sorry guys. So please, if you have any questions or comments, go ahead.
طيب انا حقيقه عندي سؤال كده بروفيسور مجدي.
Sami is talking.
نعم.
I recognize your voice from those vector quantization samples.
ده تكنيك من البيل سيستمز في التليفوني when reject كل الفريكونسيز فوق 3.4
exactly
to secure the bandwidth, and still you can recognize everybody's voice. يعني
That's
a lot
true.
of energy is being removed from the real voice. My question now,
that's true, but the new machines, right?
But it's an old technique. Remove without make just it is noticeable and recognized by other people. Except high music, and so all frequencies that above 3.4 has been removed. We are using the same technique here, and actually, I think now in this era of AI, we depend strongly on the powerful of the machine. I think we can have an intelligent algorithm, intelligent way of doing things that reducing the power. The challenge now, I think, how to reduce energy consumed by machines and depends strongly on the machine. So I think that it should be an approach, I don't know, that reducing this dependency on.
Yes, and I'm going to give you an example. You are absolutely right, Sami. So the other machine you're talking about is the physics-based. It's not like data-driven solution that's we were talking about today. I had this work to do sewage pipe inspection, which we put a robot inside the sewage pipe, and we want to detect voids, air gaps on top of the pipe. When we collected the data, we looked at it, it just looked like noise. And the hardware guys were very frustrated. They say, oh, there is something wrong with our robot, with our ground penetrating radar. So unless you have an understanding of the physics of what happened to those radio frequencies, particularly reflections, which we understand, we can model it with a physics-based model. I got to feel that this signal, the knowledge is still there. It's not just noise. We got a reflection from the transmitter back to the receiver many times, going, hitting the wall and coming back. And when you add all of them, it looks like noise. And I put a physical model to characterize, and after I model it by the equation, the physical, the old story, what's happening to the RF signals, because that's my background actually. Luckily, I was the only electrical engineering in that department, in the algorithm department. Then we figure out how to deal with it. It's just like echo. And we figure out how to remove that effect before feeding it to the machine learning. Because if I just dump it as is to the model, we were using actual support vector machine and hidden Markov models and another algorithm. We are combining like 3 algorithms to just figure out where the void is. But without this insight, here, the human insight about, that's what could be happening, the machine is going to be struggling a lot with it. So we need a helper like this layer right now for the handwriting recognition before the feed-forward neural networks. And that's always going to be the case in solving real-world problems. If you can solve part of the problem with a physics-based model, actually what we call screeners, or those kind of things are all physics-based. Whatever knowledge you have, you need to make use of it before dumping your data to the machine learning and expecting the machine learning to do anything about it, because you didn't tell the machine learning that could be happening, and you didn't provide data for that being happening yet. So solving big problems is always going to require a lot of looking at the problem from different point of views, physics-based, machine intelligence, whatever. But don't think like all what I'm trying to say. Don't say, oh, those AI tools, I don't need them. I have the physics-based model.
هو بيشبه الاكزامبل بتاع الترانسميشن اوف فويس في all telephone network in order to reserve the network bandwidth which is corresponding to the machine power we reduce the frequency to be processed. Can we do something similar?
Yes, you can, but that requires very brilliant humans to figure out to do that. What I'm saying right now, I'm giving you tools, and if you can collect data, that tools is going to help you and help the brilliant people to do more brilliant work. Does that make sense?
No, do you agree? Now it depends on the power of the machines rather than intelligent solutions.
Right, because the machine has access to huge data. It cannot fit in my brain. It can fit in a data center. So the data center
I need a lot of power consumption.
Right. Right. It needs a lot of power. That's true. But guess what? One of the demos I showed last time is how to make it power aware. So I came up with a smart power amplifier, for example. Okay,
I
we
think that
couldn't do that
I need a
by
lot
the
of
human brain. Yeah.
we
So
need
if
to
you look at
discuss
that
that more.
publication, I just Google smart power amplifier and it will show you videos or go to my LinkedIn. So we couldn't do that with our human brain.
So we engineers are liking optimization always.
It is.
Wow.
Well,
So
engineering is all about optimization and non-linear optimization.
Non-linear optimization.
But most engineers like the linear optimization because you can invert metrics and do
minimum harm to the environment. So nowadays you are making a lot of harm to environment. So we need a solution for that.
That's true. So
I don't know what the solution, but we need a solution.
Can address things that are, I'm not going to say it's impossible for the human brain, but I would say it's very difficult for every human brain to get to it. And we are building tools to help the scientists and the users.
Yeah. I think
it's like when we moved from the slide rule to the calculator.
We'll find solution one day.
It's just a new tool. You can say, I'm not going to use a calculator. It could be a brilliant person and you love using a slide rule, but somebody else is going to do it with a calculator faster and better than you.
Yes, surely.
شكرا سمحة بالنسبة is there any other comments الباقيين the iPhone عماد okay if you have and the دكتور عادل قسم الخالق okay and عماد عمر أمير and ميادة.
السلام عادل
تفضل عادل.
الحقيقة أنا ما عندي سؤال بس أنا عاوز يعني أشكر بروفيسور مجدي على البرزنتيشن الجيد جدا. الحقيقة أنا برضو ما لقيت فرصة أشوف التسجيل الفات عشان كده في شوية جاب بالنسبة للديسكشنز وبرضو أنت إذا فرصة وسلم على بروفيسور سامي. كيف حالك يا أخي؟ زمن طويل جدا. سامي شريف.
مرحبا بك عادل. And Jad, please share the slides with all the audience.
Definitely.
For sure. That's we will do that.
شكرا.
This one and this one should be shared. Okay?
Yes, for sure. Yes. All right. Are there?
Go ahead, Dr. Adil. Sorry for the disconnection. I can't hear you.
اتفضل باشمهندس عماد. Yes, عماد.
السلام عليكم وشكرا يا بروف.
وعليكم السلام عادل.
عماد معك.
عماد
وشكرا يا بروف على المحاضرة الجميلة وإن شاء الله طبعا الواحد السلايدز دي حتكون كنز بالنسبة لأي زول لأنه داير مراجعة شديدة عشان الزول يستوعب الماتيريال بتاعتها. It will not come just from the first or just glancing at it. فشكرا للعمل الجميل وشكرا لكم لكل الناس اللي جهزوا للمحاضرات دي جاد كريم والإخوة الكرام. شكرا لكم والله حاجة يعني جد ممتعة and needed at this time of the way that we are living. If you don't understand those things, you will be lost. شكرا يا مجد. سؤال جانبي ده برا انت في لوس انجلوس اريا ولا في حتة تانية؟
Yes.
ها؟
Yes, in Los Angeles area, I am close to Los Angeles, like 2-hour drive, but in San Diego City, like 2 hours drive.
نحن طبعا عندنا الدفعة بتاعتنا 87 عندنا دائما الريونيون بنعمله كل سنة في حتة، والسنة دي إن شاء الله الخميس الجاي بنكون بهناك معاكم. برسل لك العنوان إن شاء الله نتقابل.
تمام. I was talking actually to the people over there, but they didn't mention it to me. I'm glad you did.
Yeah.
Will be. It's great to be able to meet face to face.
Yeah, inshallah. Looking forward to it.
I look forward as well.
Yeah. شكرا.
Thanks.
يا السلام عليكم.
تفضل
دكتور مجدي، كيف حالك؟ كيف حالك؟
يا مرحبا يا مرحبا.
معك عبد الرحيم. يعني انت كنت يوتيوب انت لنا نحن في الثمانينات. على العموم انا بدي يعني حضرت السيشن الماضي انفورشنتلي لموضوع الشغل كده، ما قدرت احضر من بدايته، وحس اليوم برضه نفس الشيء قلت بس تكاشف عشان ترمايند يو في انه يعني صراحه كان حاجه جميله جدا يعني. فيا ريت يا اخي لو في امكانيه ترسلوا لنا اللينكس، لو عندكم لينك لها في المحاضرتين الماضي، السيشن الماضي والسيشن.
We have a video record on YouTube for the first session, and this one is going to be also on YouTube. And we have the slide deck. Jad Karim promised to share all this information.
For sure,
all
yes.
The attendance and maybe at UCANA website,
yes,
so that people can revisit it.
يا جاد كريم، كيف حالك يا أخي؟
عليكم السلام ورحمة الله.
إن شاء الله كويس. معاك عبد الرحيم الطيب.
عبد الرحيم. أهلا عبد الرحيم. يس. الحمد لله. دقيقة. أنا inviting. This is my UCANA email.
You are still recording yet?
نعم. Yes. This is my email. UCANA email. mjadkarim@ucana.org. Okay. You will see it now.
Okay. I see that.
Okay. بعد ذاك this is my WhatsApp number. Okay.
What is your WhatsApp number? I didn't see it.
It's coming.
And
it WhatsApp. Okay.
Mohandas Imad, please do the same at SRC. Share this material in your portal.
So please communicate with us, okay? And then I will also I will add your number, Dr. Magdi.
Yeah, feel free to share my contact information. My LinkedIn profile has a lot of videos, slides, and project descriptions. You will find it more useful to if you want to delve more in one specific area, you will find a specialized presentation.
جاد كريم، انا اخذت التليفون بتاعك والايميل، ان شاء الله برسلك. الو.
اي معاك.
اي فبس لك لو سمحت ارسل لنا بس اللينك على سن الزول في الشير يشوفه.
يس.
برضه يعني علقنا نعمم الشغلانيه اللي ما حضروا.
Yes, okay. So this is Dr. Magdi's number, which is 847-912-5381. So that's his.
Jad?
نعم. What's up? Yes.
Share my LinkedIn profile.
Yes.
Link to my LinkedIn. That's more useful.
So we will follow up after this. Yes.
Okay.
Yes. لو ما في سؤال أنا هوقف التسجيل وبعد ذاك. Is that okay يا دكتور مجدي؟ أنا هوقف التسجيل الآن.
If people sometimes, probably some people are thinking and they are hesitate to ask the question. Don't hesitate. Whatever in your mind, just put it.
ده جدا ان شاء الله.
أنا عندي تعليق يا دكتور مجدي على كلام بروفيسور سامي بالنسبة للكوانتم. أنا عندي بشتغل في ساعات الأتوميك كلوك دي، فالكوانتم الكوانتم عملت بريك ثرو في الساعات الدقيقة دي. فحاليا
That's true. Right.
اللي هي ذات حتى الاتوميك كلوك دي بقت تستخدم كسنسرز، بيستخدموها في الغواصات انك بتعمل نافيجيشن without the GPS for 30 days.
And guess what? More important is being used to synchronize clocks.
Yes, yeah, for single network for the communication.
Right. If you remember, I talked about multimodal. If you have audio and video, but they are not synchronized, the clock is very important for us. So I did some work on that aspect as well. But that didn't impact the technology itself. It was just consuming it. But I expect in the future that space is going to be impacted by machine intelligence directly.
Yeah.
Right?
right. أنا دائما دكتور بروفيسور مجدي ما أعرف، عندي إحساس إنه there is some relation between fuzzy logic and quantum mechanics. One could be physical, others could be logical. لكن there is some
and you know what?
In the concepts,
you just
يعني what could be physical.
If you think about Markov model, you are in a state but with probability. That's what quantum is all about.
But
in this is state or this is state or this is state, but with different probabilities.
Or maybe in fuzzy logic, the degree of membership, while
that's true. Right now we are fixing the degree of belonging to add to one. With fuzzy logic, they don't have to add to one. It's a membership. I could be member in your club and member in another club with high membership.
That is a difference. That is a difference. In quantum, we have the probability, the state probability. But there is some sort of relations. We can. I don't know what it is.
You are absolutely right, and that's an area for people to investigate. And you say you guys are not from fuzzy logic point of view, but let us give you a tool to address it from a fuzzy logic point of view.
And more relation, more research on that area. And I don't
honestly, Professor Sami, I found fuzzy logic to be extremely valuable in every project I was involved in. Even just to do video stabilization, which sounds like a job that's a chicken can do it, probably, because they have mechanism to do stabilization. But to do a control using fuzzy logic to stable
reasoning
that somebody collected from a moving device going up and down and stabilize it, I found fuzzy logic to be superior.
It's good in reasoning, domestic. In the other side, quantum is probabilistic reasoning. We have to go that deterministic and probabilistic reasoning when looking for probability. That is a feature of quantum mechanics. This feature of deterministic feature of fuzzy logic, and that can be partialized.
And you know what? My only concern as of now is just sticking with stationary distributions. And I'm trying to say, let us try those non-stationary distribution. I have a mechanism for it, because it's difficult, but it's coming. The next step in this game is going to move from stationary distributions to non-stationary distributions as needed, on the fly, depending on the nature of the application.
I do agree. I do agree.
So that's the big thing. If you stick to just a fixed distribution, you are limiting what you can do. But if you open it, you are obligated to deal with the non-stationary aspect of the model, like what we did for the Markov model. We make it non-stationary, but we have to be very creative about dealing with non-stationary distributions. And even in classical areas like in communication, when the weather change, when something like that, we need a mechanism to adapt. Right now, if you force whatever we learned statically to the communication system, is going to drop, or you are not going to be connected in severe
hot research
weather.
area, adaptive control, and
Exactly.
and it's becoming one, even in renewable energy solar systems.
Definitely, yes.
Yeah.
In all of the control systems, adaptivity is the norm, not the exception. If you don't adapt, you are not going to solve any problem in control.
The problem. That is true. I do agree.
Thank you. Thank you. Thank you. All right. So
I hope that at least I give people a discussion, a convincing discussion that this is not about chatting anymore. Although we use the chatting large language models to solve those kind of problems, but don't take it just I have a video and I came up with this singer singing this song in that voice. It's not chatting anymore. It's not that alone. But it's going to touch people in very diverse disciplines. And usually the clever part is going to having when people from different backgrounds come to solve the same problem. I wanted to do a big jump in cancer treatment. I'm not a physician. I need to sit with physicians to understand their problems. Maybe their problems is solved in my space, but my problems is also solved in their space. Unless we sit together, and that's why right now machine learning is attracting people from all disciplines, and they are contributing. Those filters that I call dilation, erosion, they came from civil engineers, and I'm a signal processing person, just cultivating what they know in civil engineering. I used it in signal processing. I think the future is always going to be like that. The old way we teach our students, you are just civil, understand civil, classical civil engineer. No, it's not going to happen that way. I talk to people from even lawyers sometimes. I talk to them. Is that what you are doing? Is that what you are doing? I can build a machine to do that. How about that? So it's a utility like electricity right now. One day is going to be just you plug into AI and you use it like electricity. Believe it or not, it's coming. And that's how the investors are thinking about it, as a utility to everybody, in every home, every office, every school, every courtroom, every lab. It's coming. I hope that I summarized.
No, you summarized it very well. And we all appreciate your contribution. And it's really outstanding contribution. So thank you. And thank you everyone who is with us. And we will send the recording, and also we will continue to update this discussion. So thank you again.
Thank you,
Professor.
And please,
thank you.
Please share. That's Why those machines are very superior? Because they share. And
They
then
sure.
they just average sometimes a model and they become more superior. So let us share.
For sure. Thank you.
Hopefully soon.
Thanks.
Thanks a lot.